Hello, my name is Amy Cohen, and I teach anthropology at Okanagan College. Anthropology includes studies of human language, human evolution, human cultural and biological variation. So here is my fact. Did you know that Homo sapiens, modern humans, share 98% of our DNA with our closest living relatives, the chimpanzees? So we only have 2% difference in the DNA between ourselves and chimpanzees. And those 2% differences account for all of the differences that you can see in human and chimpanzee physical appearance, behavior, the way we locomote, our culture, all of the things that make us unique.
Hello, my name is Stacey Sakakibara, and I'm a biology professor here at Okanagan College. My fun fact for today is that the Human Genome Project, which was the project involved in sequencing all of the DNA in the human genome, took 10 years and cost $3 billion to complete. There was a lot of DNA to sequence because we have 6 billion base pairs of DNA in our genome, but it cost a lot and it took a long time. Today, we can sequence somebody's DNA in less than a day, and it costs under $1,000. So there's been a huge growth in the technology to do this. Our problem today in genomics is that we have so much DNA sequence data that we need people with coding experience, people with expertise in data analysis to help us make sense of all of the data that we're getting from DNA sequences. So that's our problem today in biology, and maybe some of you can help us solve it.
This is your intrepid MTV field reporter, Mike, with a microbiology update. This is my friend. It's a Winogradsky column, named after Sergei Winogradsky, who was a microbiologist who studied anaerobic bacteria that utilize sulfur as both a terminal electron acceptor, but also as an energy source. Hydrogen sulfide, H2S, has hydrogens and electrons, so can be used as an electron donor for certain bacteria. Sergei Winogradsky took some mud from a swamp and put it into a big column like this. If you think about this column, there's lots of oxygen access at the top of the glass column, but if we lift up the column, there's very little oxygen available at the bottom. Also, because it's glass, light can enter the column, and any phototrophic bacteria that are in the column can use that light energy. Essentially, they're phototrophs. If you look carefully at the top of the column, right here, you see some pink to purple coloration. This pink and purple coloration is due to phototrophic bacteria that have certain pigments that allow them to absorb light that is not the purple or the pink, simply because by being that pigment, that's the light that is reflected off of them and that's hitting the camera. If you look at other points on the column, you can see some green coloration here. That green coloration is also due to phototrophic bacteria, but those bacteria have different pigments and therefore absorb different wavelengths. If we look at the very bottom of the column, right around here, you can see lots and lots of pink bacteria, which again are capable of absorbing different wavelengths of color, simply because if they are a relatively pink color, that light is being reflected off of them. This Winogradsky column is essentially like a terrarium. Bacteria at the bottom of the column are using sulfur as a terminal electron acceptor. So they're taking something like sulfate and they're absorbing hydrogens and electrons, kind of like what we do to oxygen to create water. The hydrogen sulfide, which is a waste product to these bacteria, rise up the column until it gets intercepted by bacteria up here at the top of the column that use the hydrogen sulfide as an energy source. They take the hydrogens off of the hydrogen sulfide and use them just like we use hydrogens off of carbohydrates, glucose. That is their source of hydrogens and electrons for energy production. Therefore, the resulting sulfate that's left over percolates back down the column winds up being used as the sulfur down here by these bacteria as the electron acceptor. So these bacteria breathe the sulfur to regenerate H2S. So long as the column is exposed to sunlight and doesn't dry out, in other words, we keep water in the column, this column and the bacteria in it will pretty much be self-sustaining. I hope you've enjoyed your trip out into the field and you now appreciate a Winogradsky column and all of the different kinds of bacteria that you can isolate from mud. Back to you in the studio, Mike.
Hello, my name is Doige Acosta. I'm an economics professor at Okanagan College at the Vernon campus. Did you know, or actually let me rephrase this, have you noticed that the word salary is closely associated with the word salt? Well, legend has it that the Roman soldiers were paid in salt, or they were given a stipend equivalent to a quantity of salt. This is supposed to have been called a salarium. Well, other theories speculate that it had to do with the responsibility of guarding the main trade route to Rome called the Via Salaria. But regardless of the reason, the question still remains, why salt? Well, before the invention of modern refrigeration techniques, salt was considered a precious commodity because it allowed for the preservation of food such as meat and fish. This made it a vital commodity for its strategic value. So next time that you get a paycheck, maybe ask yourself, how much salt should I be getting?
Hi, I'm Dr. Jennifer Owen. I'm the physics professor here at Okanagan College. Did you know that the largest particle detector in the world is the Atlas detector? It's located 100 meters below ground, just outside of Geneva, Switzerland, in a little village called Meyrin. It's 25 meters wide, about 25 meters tall, and 46 meters long. So in perspective, that's about 7 stories tall, and then almost twice as that wide. It weighs 7,000 tons, which is about the weight of the Eiffel Tower. And I used to work there. You can visit it too. We have tours when the particle beam isn't running.
G'day, my name is Bryan White and I'm a biology professor here at Okanagan College, and I focus mainly in anatomy and physiology. So my tidbit of information for you today, fun fact, is about bone. Now, we often think bone as being dry, dead, static, kind of like the remains of a dead tree or a metal girder in a building, something just to give us support. But bone is very much alive and very much changing. So your body has 2 types of bone cells, osteoblasts and osteoclasts. One of them will build bone and one of them will break down bone. And a good analogy is when we look at how roads are paved. So if you've ever been on the highway and you see them closed off and they're paving the roads, what they often do, or repaving I should say, what they often do is they have one big tractor in the front, right, that's digging up. So it's digging up the asphalt that's there. You've got one behind, right, that's laying down new stuff. And so they kind of go along in this tandem where one is digging it out and the other one's building it up. Digging it out, building it up, digging it out, building it up. And they go along in a pair. Well, those 2 cells that I mentioned, osteoblasts, it's the one that's building bone. So blasts build bone. Osteoclasts, they're the ones that break down bone. So they go in a group there where one is breaking it down, the clasts are chewing it up, and the blasts are building up behind it. Now, when we look at your skeleton, right, your skeleton is made up of 2 different big picture types of bones. Okay, if we look inside of it, okay, I don't know if I can see that very in focus there, but right here we've got inside of your bone what's called spongy bone. Okay, so it kind of has little holes. So this part along here is all very holy. See if I can get a better shot with this one. There we go. So right along there, that's called spongy bone. Okay, so it's very soft. It's got lots of holes in the middle. And then outside of it, we have the real hard stuff. There's a layer of hard stuff, and that's called compact bone. And so if we look at our skull here, and we look inside, okay, now it's not going to be great. It's kind of hard to see. Oh, let's use this side's better, I think. Here we go. So let's use this one. So here we can see in the middle here that there's spongy stuff right there, and then there's a layer outside of it of hard bone. Okay, so it's kind of like sponge toffee. If you ever had sponge toffee, you bite into it and there's a hard layer on the outside and a spongy kind of holy layer in the middle. Well, it's always being remodeled by these two little guys that are traveling around chewing up and laying down. So after you're an adult, your skeleton is its full size, so it's kind of full adultly grown skeleton. The spongy stuff is replaced in your body every 2 to 3 years. Whereas the compact stuff, the hard stuff on the outside, right, that layer of compact, it's replaced around every 10 years. So every 10 years, you have in essence a brand new skeleton. Now, it'd be great if we could get them to make it bigger and stronger, hey, we can keep growing. They don't. They just replace it as it is now. So it's kind of like saying someone takes a painting and makes a copy of it. They're not making a new one, they're not making it better, they're just making a copy of what's there. But you have a brand new replaced skeleton every 10 years. And that's my fun fact of the day.
Hi, I'm Dr. Carpenter, and I work in the psychology department at Okanagan College. I am an academic social psychologist by trade, and I'm particularly interested in social ostracism. You're probably familiar with the experience of being ostracized, that is, being left out of a group that's important to you. But do you know why it's so painful? The simple answer is we partially define ourselves based on the groups that we're a part of. So when we are left out of a group, it feels bad because it feels like it's an attack on us as a person. A little bit more in depth, what being ostracized leads to is a decrease in sense of belonging, a decrease in self-esteem, a decrease in a sense of control, as well as a decrease in something that psychologists call meaningful existence.
Hi, my name is Doige, and I teach chemistry at Okanagan College. And my fun fact related to chemistry is related to an odor that's referred to as petrichor. This is the earthy scent produced when rain falls on dry soil. Now, have you ever had a situation when you've been out and the soil's been relatively dry and then it rains? And then you notice that there's this smell in the air. And sometimes we say, oh, that smells like rain. Well, in fact, it's not the rain that you're smelling here, but it's the chemical called geosmin. And you can see a structure of this chemical on the right on the slide. So scientists believe that the smell that we detect is this chemical. And this chemical is produced by soil bacteria. So when water penetrates the soil cavities, the water facilitates the release of this chemical as an aerosol, and then you detect it. Now, what's really remarkable is that humans are able to detect this chemical at levels less than 10 parts per trillion. Now, compare this to the detection of blood or other organic material by sharks, which is more at the level of 1 part per billion. So humans have evolved to detect really tiny amounts of this chemical. Why might this be the case? Well, scientists believe that early humans evolved this ability so that, in fact, they could detect water, because, of course, small levels of this chemical is also related to the presence of water. Now, you may also be interested to know that this chemical is responsible for that earthy taste in beetroots. So if you love beetroots, maybe it's because you love the taste of this chemical. I hope you enjoyed finding out about petrichor and geosmin. Bye for now.
Hello, my name is Matthieu Caron. I am a professor at Okanagan College where I teach history, notably global history, Canadian history, and BC history. Did you know, for example, in BC history, that for a number of years, there was a gold rush in the Fraser Valley, in the Caribou region, and in fact, this gold rush brought camels to British Columbia. The camels were thought to be a bit better suited to walk the rocky conditions that British Columbia has to offer as opposed to mules or horses. But they frequently became stuck and left holes in the terrain, which left this entire scheme to bring camels into British Columbia quite a failure. Eventually, a court injunction banned camels from British Columbia's roads. And the entrepreneur who brought these camels just left them to roam in BC's wilderness. And for years, for about 30 years, people would see these camels appear out of nowhere. This happened between the 1860s and 1890s. I hope this tidbit of British Columbia is the type of trivia that you enjoy. And if you do, join me in one of my classes. Thanks.
Hey everyone, my name's Bob. I work at Okanagan College with Chris. Did you know? Good God, I've lost half my head. Let me help you out a little bit. Ta-ta. Hey, I'm Chris. I teach Biology 12, Human Anatomy and Physiology here at Okanagan College. Yeah, great place. Did you know that your ears never stop growing? I've heard there's maybe some other body parts, but it might be wishful thinking. I hope my nose doesn't continue to keep growing. You produce about 40,000 liters of spit in your lifetime, or put it another way, that's kind of like around 500 bathtubs, if that's at all appealing to you. On the average, your nose produces about a cup of mucus a day, and you pass enough gas on an average day to fill a party balloon. Might not be much of a party for everybody else, but and you wee enough to fill about a bathtub every month. So those are some pretty cool facts about human anatomy and physiology. Maybe I'll see you up here.
Hi there, I'm Melissa Munn, and I teach in the criminology department at Okanagan College. Did you know that this guy was booked and paw printed at Eastern State Penitentiary in 1924? His real name was Pep, but he went by the alias The Dog. He was booked and given a life sentence for cat murdering. The fact of the matter was, Pep had never killed any cat, but people around the world were outraged to think that this poor puppy had been given a life sentence, and the governor at the time and his wife received letters from all over the world condemning the action and asking for a pardon and forgiveness for Pep. The reality of the situation was the governor knew that the conditions at the prison were terrible. They were overcrowded, just like they are today. Morale was low, just like they are today. And so he decided to send one of his most loved dogs, this beauty, Pep, in to be a morale booster. And it worked. However, just like we know, zombie facts stay. And so it took a long time of him doing interviews to convince the public that Pep wasn't being held against his will. In fact, he was having a pretty good life. The only problem they had was he was getting a bit fat from everybody sharing their food and giving him too many treats. So he spent a few years at Eastern State Penitentiary, and then he was eventually transferred to another prison where he lived out the rest of his life and was buried on the prison grounds in his favorite flower bed. So there you go. Now you know.